exact eyes. Oh, it's a different department. Not yet. Yeah, kind of like it's the goal. Fun. Yeah. Are you on? Oh, yeah, right. I knew that. Yeah, Noah. You know, my dad went to that. My dad tried to get me to go to Hopkins.
All right. Welcome to the GRASP seminar. I am standing here because Pratik Chodari is stuck in India, our colleague from Electronics. He was supposed to introduce. Joshua Vogelstein is faculty at Biomedical Engineering at Johns Hopkins. He did undergraduate at WashU, and then he did a Ph.D. in Neuroscience at Johns Hopkins, and he spent lots of years both at Hopkins and at Duke, and working also in applied math and statistics. He has very foundational results in machine learning, and today he's going to talk to us about lifelong learning.
Thank you. Hi, everybody. Thanks for having me. I'm really excited to be here. So yeah, I'm going to talk about lifelong learning and moving beyond avoiding catastrophic forgetting. Can everybody hear me? Okay, cool. So just going to start with learning. Presumably, for most of you, this will be relatively mundane and overview, but it's important, I think, to get the basic foundation of this before we build on it. So there's been lots of work on trying to define what learning is. There's a work from Batnick in the 70s and Valley in the 80s, and then Tom Mitchell wrote this really classic book in, I guess it was in the 90s, the first edition. So Tom Mitchell defines learning as follows. This isn't an exact quote, but it's close. An agent F learns from data D with respect to task T with performance measure E if F's performance at task T improves with D. Okay, so it's a nice colloquial kind of thing. It's approaching being a relatively formal definition. I'm going to try to make that more formal now. So we're going to say generalization error is the performance measure that we care about. And so generalization error is the expected risk with respect to the training data set. So D is the training data set. F is an algorithm that's going to be the learning. So F eats the training data set. R is the risk. It could be, say, the expected loss or something like that. And then this expectation on the outside is the expectation over different possible training data sets that you got. And so this is kind of a standard measure of performance in machine learning. And it's just, like I said, it eats F and D. So there's an algorithm and there's a data set, and it's a function of the task. And we indicate that by this little T. So we say F learns from data if it's the case that the performance when F gets D sub n samples is better than, in this case it's expected loss, so it's smaller than the performance when there's zero samples, so when n is a zero. Okay, so you have some performance in your algorithm, maybe you've encoded some prior knowledge, maybe it had some other data, who knows, it's just an algorithm it spits out a decision rule, and then you give it data and it updates the decision rule, and now it's learned if it's doing better. Okay? Okay. So here's the simplest example I can think of, and we'll build up from this obviously, but we have a two-class classification problem. We've got purple dots and green dots. We're going to observe 100 points. Each point is in 2 dimensions, and we want to learn a classifier. It's going to discriminate between the two classes. So here's the dots. You can see the green dots are more on the top right and the purple dots on the top left. So learning here would be learning a discriminant boundary between the two. It turns out we set this up. The optimal discriminant boundary is this line. And so what that means is the learner has partitioned this 2-dimensional feature space into 2 partitions. And then if there's a new point, what it does is it sees which partition it lands in. And then if in that partition more of the training data are purple dots, then it says, okay, this one is a purple dot. And if in the partition more of the data are green dots, then it says, okay, this is a green dot. This is just basic, essentially all possible classification algorithms do that. To put that into words a little bit more, what a classifier does is it learns 2 things. First it learns a partition of feature space into parts. And then it does a majority vote of all points, and it assigns to each part a class label. Now, when you're trying to make a prediction, the first thing it does is define which parts it's in, and then it finds what is the majority vote in that part. Okay, so this is all of classification. I gave you a two-dimensional 2-class problem, but it generalizes. Everyone's with me so far? Okay. Now regression, you don't have to think of it this way, but you can also think of regression this way. One can solve a regression problem as follows. First, you partition space into parts. And then say, at each part, you take the average of all the points in that part as its prediction. And so, again, if you got a new point, first you find out which part it's in, and then you just find what is the average in that part. It's not the normal way people think necessarily how regression works, but it's a perfectly valid way of doing regression. And there's a really fundamental theorem in statistics. It's from Stone, 1977. And what Stone says is, if you try to solve a supervised learning problem this way, either classification or regression, and you have 2 of the following conditions. First of all, each part is small enough, and second of all, there's enough points in each part so that you can get a good estimate of who's the majority or what's the expected value, then given enough data, your risk, your expected, your generalization error will converge to Bayes' optimal performance. Okay, so the reason I call this a fundamental theorem of pattern recognition is this tells you, in general, if you don't know anything about your data, you're going to get a bunch of it. If you design your function to have these 2 properties, then you know with enough data you will get the best possible answer. Okay? And I want to note that these parts, they don't have to be non-overlapping. So for example, K-nearest neighbor is an instance of this, and in fact, Stone's proof really focused on the K-nearest neighbor. In K-nearest neighbor algorithm, each point partitions space around it, but those partitions are overlapping. Compare that to something like histogram rule, where in histogram, all the parts are non-overlapping. Both of these are perfectly fine examples of partitioning space, and both of them have this property that as long as the partitions get small enough and there's enough points in them, then they'll converge to beta. Okay? Alright. So that's all kind of basic machine learning. Then people start talking about transfer learning. So what's transfer learning? Now we're given a data set V0 and an algorithm F0, which is trained using only that, only that data. Now we're going to get data which includes those data points and a whole bunch of other data points from some other distribution. I'm going to train that same algorithm to use all of the data. I was saying an algorithm transfer learns from data Dn with respect to transfer learning task T with performance measure E if S performance at task T improves with Dn. In other words, it's the exact same equation as we had before. D0 is just some source data, maybe, that you happen to have, and then you get a whole bunch of other data, and the point is, if that whole bunch of other data, regardless of what distribution it's from, if it helps you, then you transfer learn from this other data set to the target task. You guys listening? So this is not obviously the way most people think about transfer learning, although it's a natural way to think about it for me. But just, if you don't understand the slide, let me know if it's a pretty important conceptual slide for what follows. Yeah?
What's the difference between this
The difference here is that the data in D0 could be sampled from a different distribution than the other data. And in the normal setting, like any theorems you have, the assumptions are that all the data are sampled from the same distribution. That's why you have to transfer. Yeah?
There are other ways to measure transfer. For example, you learn faster or...
Right, so there's an n in here. So there's a rate is implicit in this definition. Okay, so this is a definition of transfer learning. Multitask learning is a generalization of transfer learning. Now there's not just one, say, source data set and then a target task. Rather, there's many target tasks. And what you want to do is use all of the different data sets from each task to improve performance on all the other tasks. Okay, so we have algorithms Fj, each of them are trained only on Bj. So Bj is the data corresponding to task J. And then we're going to have an algorithm Fn, which is trained on all of the data. And then we say F multitask learns if basically the same thing. So I've introduced you two different possible definitions of multitask learning. One on the top is we could say F weakly multitask learns if on average the performance over all the tasks once you've done multitask learning is better than you would have done if you treated each task independently and just learned on it. Right, so you can have the average performance on single tasks, and then you can have your performance overall using everything. So that's a way of saying that you multitask learn. A stronger thing to do would be to say for every single task, you do better by virtue of including data from all the other tasks. That's a very strong restriction, right? That means no task could do worse by virtue of having other data sets. And so in machine learning literature, people talk about this often as catastrophic forgetting. If you get data from a new task and you do worse on the other tasks. And so this would say you have no forgetting whatsoever, right? Every single task you get better at by virtue of seeing data from other tasks. Yeah.
Is it that argument saying that here D sub n is the union of D?
Yes. That notation is that. Okay. Okay, so lifelong learning, I'm going to say, is a generalization of multitask learning. It's different from multitask learning in two ways. One is that the data arrives sequentially, and so you don't just get all the data all at once. And the other is that there isn't a fixed and finite capital J. Like there's no notion that there's only J tasks. There can be an infinite number of tasks as long as there can be an infinite amount of data. Okay? So now we're going to say lifelong learning. The criteria for saying whether something lifelong learns is very similar to multitask learning. In fact, it's the exact same equation as we had in the previous slide. It's just that the way that the algorithm gets data is now sequential, and that it doesn't know the number of tasks they prioritize. You have to be able to use your performance on the past task to make out-of-task predictions on future tasks, tasks you haven't ever seen before. So the algorithm has to do more work, but the definitions can be the same. Yeah?
Why didn't you consider the permutations of the ordering?
Yeah, so it's a great question. The question was, why didn't we consider the permutations? The answer is that they makes it much harder, is one, and also, in a certain sense, we're conditioning on a particular sequence of the data, and so they kind of
So we should understand that these J's are actually ordered.
they're ordered down. That's right. Yeah, in the previous slide they were not ordered, and this slide they are ordered. So implicit in that, what you'll see later, it's straightforward to generalize, but I'm going to assume later that all the data from task 1 happened, then all the data from task 2 happened, then all the data, etc. You could obviously just say at each sample, you sample data from one task, and then the next sample could be from a different task. But for simplicity now, it's easier to think about it like that for me. Okay. So evaluation criteria. We talked a little bit about this before, but I'm just defining transfer efficiency as follows. So you give it a random data corpus, let DJ denote the set of samples that correspond to the J task. The transfer efficiency of an algorithm F for task J is defined like this. So this is the ratio of the performance it achieves when it only uses the data from task J relative to use all the data. Okay, so that's transfer efficiency, and it corresponds to this thing about, the question about converging faster. It literally is basically what it means is it's converge faster. Both of them have the same amount of data from this task. But if you give it a bunch of other data, it gets performance better, so it has converged faster in a very good way. Okay, so that's what we're saying transfer efficiency is, and an algorithm F transfer learns if this is bigger than 1 on that test. Okay, now, an interesting thing to me, because now we're in this sequential setting, is we can talk about forward and reverse transfer. Okay, so forward transfer efficiency, conceptually, we have task J, and it measures the improvement on task J resulting from all data preceding the last sample that was from that task. So you have a bunch of data, some of it's from this task and some of it's not, but some of it may have come before you've seen this task. This is kind of the classic transfer learning setting where you have some source data you transfer forward to this target task. So there's a bunch of notation in here, which, is a little take possibly for a talk, but the point is that the transfer efficiency, forward transfer efficiency, I'm defining here as on the top we have the performance on task J when it only got to use data from that task. And the bottom is the performance on task J when it got to see all the data up to and including that task, but no data later. Okay, and so if this is bigger than 1, then you forward transferred. Right? That means you use past data to improve performance on future data. And it's a very natural and easy thing to do. Say if you're in a neural network, you train it on a task, now you get a new task, you initialize the weights with the parameters that you learned from the first task, and you just update them. That you would be comparing that to, say, some random initialization, and often that works very well, and it's really not problematic in learning in general. So forward transfer is relatively easy. But reverse transfer is not. So reverse transfer is a different thing. We have task J, and then we're going to measure the improvement on task J resulting from all data occurring after the last sample that was from task J. Okay, so now you've trained up your thing on task J. And now someone gives you a bunch more data later. So what you'd like to happen, if you're going to be a super efficient learner, is all that data that happens later improves performance on all the previous tasks you've seen. But why shouldn't it if those tasks are somehow related? They should be able to improve it. And so we can define reverse transfer efficiency as the similar ratio. This is the ratio on the top is the performance of your algorithm on task J given all of the F's of J, is basically all the past data, normalized by seeing all the data, including all the future data. Okay, and so this is, as far as I know, a new notion. And the thing that's really nice about it is this transfer efficiency factorizes. You can see the definition of transfer efficiency on the right. It factorizes into these two terms. So the product of forward transfer efficiency and reverse transfer efficiency just gives you transfer efficiency. And so it's a nice way, I think, when you're in this streaming setting, to think about how much your algorithm is benefiting from past data and how much it can benefit from future data. So I would just relate this concept of reverse transfer to catastrophic forgetting. So catastrophic forgetting, it means you got new data for a new test and you forgot how to do the past test. And there's been lots of work in the last 30 years on avoiding catastrophic forgetting, right? So when you avoid catastrophic forgetting, that means you get new data from a new test and you don't get much worse than the past test. But if you think about it for a second, that's not enough. Right? First of all, it's not what biological systems do. If I get data on a new related test, I can improve performance on the old test. And why wouldn't I want to be able to improve performance on past tests given future data? Those past tests could show up again. Right? So I think trying to avoid catastrophic forgetting is really a short-sighted goal in a certain sense. What we want to do is actually achieve really efficient reverse transfer. And I would argue that to achieve artificial general intelligence, we really need to do it. Otherwise, we're not using the data as efficiently as possible. And one of the nice things about biological intelligence is we really do that. So,
Are you assuming that there exist loss functions that would make this possible for some corpus of data? Because you could imagine data where there's no such.
yeah, I'm going to talk about adversarial tests and how that screws things up. And so that's related. It doesn't exactly answer your question about different losses, but you can set up different tests so that you definitely.
But you needn't consider those adversarial. There are data and functional relationships that are intrinsically multimodal and have rugged landscapes. I'm not sure why you would call that adversarial necessarily.
I'm calling it adversarial, I think you'll see, is because it makes you forget previous tests. And so if I wanted you to forget a previous test, I could design a new test that would degrade your performance. So an adversary would do that, I guess. But non-adversaries might just be complicated and unrelated and also improve your performance. Yeah. Okay, so, I'm saying we want this, but is it real? So I'm going to just say two things about that. One is, if your tests are complex and they're built of subtests, and you have a future test which has an overlapping set of subtests and past tests, you get training data for the future test, and you can improve performance on an overlapping set of subtests. You should get better on the past ones. Just, for example, I have a 5-month-old baby. She's learning how to put her pacifier back in her mouth now. Once she learns that, it's going to be really easy for her to learn how to scratch her ear, and she's not going to forget how to put her pacifier in her mouth. And the reason is there's lots of things she's had to learn along the way to do it. How to control the joint in her elbow, and her shoulder, and her wrist, and grasp. All those things are subtests. Once she learns them, that's great. But now she can practice them in lots of different configurations and get better at putting her pacifier in her mouth too. Because right now she kind of can do it sometimes, but often she just cries until I put it in. Once she practices grasping other things and putting things in other places, she'll get better at this too. And it's not just anecdotal. There is real data to suggest that humans do this in lots of motor behaviors, but also more complex cognitive things, like in language. So there's some evidence that if you learn a language and then you learn a second language, it improves your performance on various measures on the first language. And people who like teaching multiple languages talk about this all the time. Yeah.
I'm not sure the language example is a good one, because I guess the thing that pops to mind is false friends. For example, words that you'll use words in the first language and try to use the equivalent in the second language. And so the example that comes to mind is I had a French teacher once who tried to ask if his food had preservatives in it in French. But in French, the word preservative means condom. So he was asking if there's food with condoms in it. So I guess there are examples where using stuff you learn from the first language can be detrimental, or as you're saying, adversarial, where you're trying to use in the second language.
Yeah, I think that's true. And so the performance measure is integration over all the things, right? So just because it hurts you sometimes, I'm saying overall it helps. That doesn't mean it doesn't hurt anywhere. And so I don't know this literature particularly well, but these guys believe that it's true overall, and we can fight about it with them. I don't have a fight in this stake. There's lots of very simple motor learning tests where this obviously happens. I mean, just like the example I gave you with controlling your hand, you can do that. Okay. So what is lifelong learning? So now I'm going to say a algorithm lifelong learns if, for all tests, if both forward and reverse transfers. You'll see why I'm going to define it that way. But it's one of many possible definitions. I'm not saying it's the right one or the best one, but it is a fine one now that we have this conceptual repertoire, including forward and reverse transfer. Okay, so I argue that brains do it, maybe not, but I think they can. But there's a natural question of, can AI do it? So McCloskey says in '89, training on a new set of items may drastically disrupt performance on previously learned items. This is one of the first times people acknowledge the possibility of catastrophic forgetting. And that was 30 years ago. This is a few papers from the last couple of years. One of them from DeepMind. Published in PNAS, where they're trying to avoid catastrophic forgetting. And the point is, it's been a big deal, and people have really tried to overcome this for a long time. There's a few choice quotes from people. So this one of those papers, the DeepMind paper, 2017, achieving artificial general intelligence requires that agents are able to learn and remember many different tests. Not exactly saying reverse transfer. In fact, none of these quotes are exactly saying you need to do reverse transfer, but it's close. Gary Marcus, you guys may know him from trolling Jan LeCun and Bengio on Twitter. He says, we shouldn't absolutely start over from square one in every domain that we confront if we're going to reboot AI, right? So if you guys read the cognitive science literature in the 50s, the leading model of cognitive science was this tabula rasa model. It was advocated by all the empiricists, which said you're born knowing nothing, and then you learn everything through experience. And a lot of people debated that, including, say, Chomsky, which was this nativism perspective, where you're born knowing a bunch of stuff, and then you learn more. And in retrospect, that camp was obviously right. For example, let's just take a deer. When deers are born, they know how to run. They get up and they start running. They didn't have to train. They didn't have M training samples or whatever. They just run. And they get better with time, but they know it when they're born. We actually know lots of things when we're born. We know how to suck our thumbs when we're born. We know how to breathe, move. We know how to cry when we're unhappy. So it's not the case that we learn everything from nothing. But that is the current essentially established framework in machine learning, where you start with nothing when there's a new test, and then you try to learn. Judea Pearl also points out, he's talking about the limitations of kind of, well, not causal reasoning in general, but also just modern, he calls it narrow AI. And one such obstacle is adaptability or robustness. Intensive theoretical experimental efforts towards transfer learning, domain adaptation, and lifelong learning are reflective of this obstacle. The point is, I think it's a really big problem, and a bunch of people that I respect a lot agree. It's also a real industry challenge. So take Amazon. Amazon has a recommender system. But tomorrow, there's 1,000 new products on Amazon. And there's 100,000 new reviews on them. What Amazon would like to do is update its system to include all those new products and not forget all the past performance. Right? And so, but more than just not forgetting, it would like to use all this additional information from new products and new product categories to improve its recommendations on everything. This is the problem. As far as I can tell, Amazon hasn't yet solved. Google is the same deal, right? There's another recommendation engine. In healthcare, there's lots of reasons where you would want this. There's new diseases to find, there's new tests, there's new assays, there's new treatments. If you're doing kind of AI for personalized medicine or precision medicine, you really may want to update your model for when all these things come in, rather than getting a whole new data set and having to train all over again. Augmented reality is another example. So my brother started a company called Mindex, and they're working on this augmented reality thing. But you can imagine in augmented reality, you want to be able to have a model of the world that is constantly updating itself, even though you're doing lots of different tests in the world, and to have some kind of interface that allows you to learn from all of that. The AI will learn from all of that and help you make decisions about how to proceed. So there's lots of applications, there's lots of good reasons to want to solve it. Here's a proposed, I think, relatively, arguably very straightforward algorithm for doing it. It goes like this. For each training data set, the first thing you do is you learn a new partition. We're purely in supervised classification setting for this example, but it generalizes. You learn a new partition from that. And then you learn the most likely class of each stuff. Then, for all the previously learned partitions, you push all the data into them, and then you identify where they live with respect to that. So in other words, you estimate the posterior probability in each part on all the different tests you've seen, including all the past tests. And then at the end, you take a majority vote across all of the partitions. Let me try to show you a schematic of how that works. You have data set 1.
Could you say how this differs from Lloyd's algorithm, generalized Lloyd's algorithm for code generation, adaptive code?
Yeah, let me go through this slide. I think it'll be clear, and if not, then that's it. So, data set 1 comes in subset of the data from which you learn the partition. And this ends up being really important. People pointed this out. Brian pointed it out in '84, and then people forgot, and in 2014 they remembered. If you learn a decision tree, normally the way people do it, you take a bunch of data, and you learn the partitions, and then at the end of the partitions, you evaluate that you take a majority vote for all the data you used to learn that partition. It turns out if you do that, and you try to estimate, therefore, the posteriors in each cell, you've overfit, and you're biased. And the reason for that is relatively straightforward. Typically, the rule for when you're going to stop partitioning is when each leaf is pure. Okay, and so that means if you were to take majority vote, you would say there's a probability, it's essentially deterministic in each cell which class you're in. But in general, that's not true of data, right? These cells are ambiguous and they're probabilistic. And so if you do that, you really end up overfitting and having a strong bias in your probabilities. So what you have to do is partition, I shouldn't say that, you subset the data. On one subset, you learn the partition, and on the other subset, you're voting in that partition. And that's what you do for just one test. If there's only one test, there's no aggregation, you're basically done. But once you get another data set, on that data set, you learn a new partition, totally ignoring the first partition. Now you can use all the data from the first data set, you can push it through that partition and see what are the majority votes for all those classes. And you can take a subset of the data from data set 2 that you didn't use to learn this partition, and you learn the posterior likelihood posterior probability for each cell in there. And now you have 2 estimates of posterior probabilities, one from partition 1, one from partition 2, and that's where you aggregate them. And that's how you would do the forward transfer. To do the reverse transfer, you take all the data from data set 1 and you push it through partition 2. Now you can estimate the posteriors from partition 2 using all of the data from test 1, because you don't have this bias, because it's all essentially out of bag. And now you have another estimate of the posterior probabilities for all the data in test 1. And then you can aggregate that and you can make a prediction. Okay, so the key is just realizing that you get to make 2 different data sets essentially for each task. And you can use them to learn different things. And assuming the partitions from task 1 are informative with regard to task 2, then you will do better. If they're not informative, then you could do worse. And I'll show you examples of that. So does that answer your question? Okay.
So you assume the feature space is shared across.
The feature space is shared across everything. Yeah, that's a limitation for now. It doesn't make any assumptions about the class labels being shared. They can be shared or not shared. I'll show you examples of that. Okay. So here's some simulations. This is the simplest simulation I could think of, and it's one of my favorites because it's contributed to the first AI winter, which I think is really. Okay, so XOR, right? XOR, the classic XOR is you XOR gate, right? You want to say the 1 if it's a 0, 1, or 1, 0, if it's a 0 if they're both zeros or both. Okay, so I'm saying the data lives in 2 dimensions, and it's going to be a 1, or in this case it's going to be green if you're in, say, the odd quadrants of this feature space, and it's going to be purple if you're in the even ones. And that's XOR. So you get a new dot, depending on which quadrant you're in, that tells you whether you're a 0 or a 1 or a green. Now consider non-XOR, which is the same partition of space as XOR, but it's a sign flip for the class labels. So now purple is in the odd quotient and green is in the even. Okay, so the reason I think this is an interesting example is because they're literally the exact same optimal partition. In other words, if you learn a partition for task 1, you have also learned a partition for task 2, and vice versa. So it's kind of the easiest setting you could possibly imagine for transfer learning. And so here's the results. I'm comparing a few different things. So uncertainty forest is our approach where we do this splitting of the data for just one task. And you can see on the x-axis, I'm plotting the number of samples of XOR. And on the top right, the generalization error the x-axis is the number of samples for non-XOR. And on the top right, I'm plotting the error for XOR. Well, you can see is using both. It uses the partitions from XOR and the partitions for non-XOR. Because it's the same partition, it can benefit from using both of those. And what you can see is the red line is doing as well or better than either approach, regardless of the number of samples. And that's true both for prediction generalization error in XOR and its generalization error for non-XOR. Right, so by virtue of using the partitions that you learn from both, because they're so closely related, in fact they're the same, you can do much better than using the partitions from just one or the other. Okay? So here's a very closely related example. It's a spiral example. The main thing to point out here is, in the top is two classes, the predictions, and the bottom is 3. And so you might think, oh, to do well in this 2-class problem, you need relatively coarse partitions, and the 3-class one, you would need finer partitions. So there maybe you can't transfer as efficiently. But the basic result is the same. In both cases, if you can use partitions from both, the XOR partition, the 2-spiral partitions help the 3-spiral, and the 3-spiral help the 2-spiral. The intuition underlying this is in both cases you're actually way over partition space because we're using really deep trees. And so the fact that you could have a much coarser partition, we end up having relatively fine partitions in either way. And so it helps. It helps even though there's a smaller number of classes and therefore the partitions are more close. Okay. Here's what I was calling an adversarial test, although maybe we should just call it another test. On the bottom left, I'm showing rotated XOR. So here I've rotated the data by the coordinate axes and everything by 45 degrees. Now the reason that's an important consideration is if you look at the top right orthant, there's literally no information in there about whether you're a class 0 or class 1 with regard to rotated XOR, because it's 50-50. In fact, every orthant, if you just look at the partition from XOR, is wholly uninformative about what's happening in rotated XOR. And vice versa. If you look at the optimal partitions in rotated XOR, they're wholly uninformative about XOR. And so it's not obvious one should be able to transfer anything in this setting. And indeed, what I'm showing in the top right is the performance of the lifelong learning bars on XOR. When you try to use rotated XOR, actually the performance degrades a little bit. You get worse than if you totally had ignored the rotated XOR. On the other hand, when you're trying to make predictions about rotated XOR, we're still doing okay. So lifelong learning bars isn't suffering too much. So the point is that we are still forgetting. It is not the case that in this setting it's impossible to forget, but rather you can design adversarial tasks that would make it forget. And therefore it's not totally safe to adversaries, it's not totally robust in that way. But the nice thing is it doesn't catastrophically forget, even in the most possible uninformative task. It does a little bit worse. And in fact, what we can show, I think the interesting plot here is on the right. Here we had task 1 was XOR, and tasks 2 through 9 are all rotated XOR, rotated at 45 degrees. So every single additional task you get is wholly uninformative about task 1. And what you can see is that transfer efficiency is kind of gracefully getting worse, rather than catastrophically forgetting. And you'll see why that's important in the next slide when we compare to some other real examples, how bad catastrophic forgetting can be. The point is it's not actually catastrophic forgetting, but it is forgetting, and it's sensitive to that kind of thing. Okay. Assuming that stuff is clear, I want to give you the real data examples now. Ready? Okay. So this thing called split CFAR, or CFAR 10 by 10, we take the CFAR 100 data set, I'm sure you guys are very familiar with it, and we split it into 10 different tasks. So for each of the 10 tasks, there's going to be 10 classes. In each class, there's 500 training samples and 100 testing images, and all the images are 32 by 32 color images. Here's some examples. This is actually the examples from the CFAR 10 rather than CFAR 100, but it gives you a good idea. Categories are things like airplanes and automobiles and those kinds of images and the kinds of resolution that we have. Okay, so what we're going to do is we're going to train on task 1, and then we're going to update performance using task 2 data, and then we're going to update using task 3 data, etc. We'll do that for a bunch of different algorithms. Just to give you a perspective, there's a really nice paper I thought called Progressive Neural Networks in 2016 on the archive from DeepMind people. And this is, I'm not quantifying transfer efficiency. This is a plot from Figure last year that evaluated the stuff on the CFAR data. And what you can see is each line corresponds to the performance of a different task. And as you can see, for each task, as you start training, you start getting better and better accuracy. And then when data comes from a new task, it doesn't catastrophically forget. It stays the same. It doesn't get better, but it also doesn't get worse. And they were very excited about this result because they've avoided catastrophic forgetting. You can see the subsequent ones are getting worse, and they didn't really explain that, but it is what it is. This is them avoiding catastrophic forgetting. Now I'm going to show another plot. Excuse me, the legend is over the stuff. But here, now the y-axis is forward transfer efficiency. This is the ratio of performance of the single task that you only gotten tasks from that data relative to you've seen all the previous tasks. And what you can see is this progressive neural net thing. It turns out that it's not really helping very much until the very end when you look at it this way. And this is compared to a whole bunch of other approaches, all of which were published after that paper. In fact, the progressive neural net paper was only on archive. They're all kind of doing forward transfer. And again, forward transfer is very natural in neural networks. You update your parameters based on having just trained it from some related data set. You should do better than if you had just started from random initially. So all the different algorithms are doing forward transfer. And in fact, they all end up at about the same place. So the cumulative forward transfer is about 1.24 for everything. So that's fine. Our lifelong forest is the red line. It's kind of in the middle, but they all end up about the same place.
So in terms of the classification task, after the second task is coming, is the union of classes or just a new class?
Just a new class in this particular thing. Well, in the code for us, it can be whatever. This example happens to just be just the new ones. Okay, so now we're going to look at reverse transfer efficiency. So remember, that's the ratio of single test error to error using all the future tests as well. And we're going to have a line for each test, for each algorithm. And if the line is increasing, that means the algorithm is achieving reverse transfer. And if it's flat, it means it's not. And if it's decreasing, it means it's catastrophically forgetting. So here's all the algorithms on this test. And what we can see is several of the algorithms are just catastrophic forgetting. You get another test, and your performance drops by 20% on the first test. Some of them are not dropping by 20% after one test, but many of them are dropping by a lot. The progressive neural net is the black line. It's totally constant because you saw before it never got any better on previous tests when we got these. The red line is lifelong forest. What you can see is, on average, in general, anytime you get new data, it improves performance on all the previous tests. Right? That's every single line is going up as it gets, in general, data from any new test. So you just take test 1. Once it's seeing test 2 data, performance on test 1 is up by like, I don't know, 8% or something. Test 3 data is up another few percentage points. Eventually you get up to like 20% improvement. About 20%. Yeah.
Did you also compare the absolute performance numbers?
Yes, I did. I don't think that slide is here. Most of them are doing pretty crappy, like 30, 40% accuracy. We're in the middle. We're like at 50 or 60, I think. Progressive neural net is much better. It's like 70 or 80%.
But that also kind of affects how much of a room there is to improve.
It does, and but that's true, and this ratio normalizes for that, right? So because we're dividing by your performance at test 1, if you're doing much better, so if you're at 50% accuracy and you get to say 60% accuracy, about the same as going from like 90% accuracy to like 92% accuracy, based on how the ratios work out. So we've tried to account for that in the actual metric. So is this plot clear? I hope it's clear. The sentence at the bottom tries to make it very clear. Only lifelong forest is good at reverse transfer, as far as we can tell. But just to be clear, we didn't write any of the code for any of the other things. We just found the code online for those implementations. So I'm pretty confident it's not because we ran their algorithms wrong. because we ran their code with essentially no modification other than changing the input, which made us have to change the number of features for the inputs, but otherwise. Okay. So this here's just a table of this final or cumulative forward transfer and reverse transfer. You can see we're doing as well or better than everybody with regard to the forward transfer. And with regard to the reverse transfer, no one is doing better than one except for us, we're getting about 20%. Now, on the right I'm showing a different number of parameters for the other algorithms. It's not that clear, honestly, how to compute the number of parameters for our thing, because how many parameters go in a random forest? So I computed a range. The basic intuition behind this is as follows. For each node of the tree, for each task, we have a 9-dimensional parameter, which is the probability of each of the tasks, but each of the classes, because it has to sum to 1, so there's only 9 degrees of freedom. And there's 10 of them, so there's 90 parameters per node. It turns out that each tree has about 600 nodes, so you can think of that as like 60,000 or so parameters per tree, basically. And then we have about 10 trees per thing, so you do the multiplication. You can think of that as actually having 20 million parameters, but you also think of it as only having 500,000 parameters, because once you have more than one tree, you're really regularizing. That's the point of having multiple trees. You're kind of regularizing a tree. So I don't know how to count the number of parameters. What I know is the number of parameters is increasing for us, and it's increasing linearly with the number of tasks. That's also true for the progressive neural net. It's true kind of for EWC because it has this regularization term, which is increasing linearly the number of tasks. The other ones are not doing that. But whether it's 500,000 parameters or 20 million parameters, if you just compare, say, the transfer learning from task 1 to task 2, it's clearly less than 1 million parameters for us, and we're clearly doing reverse transfer efficiency, and it's also clear that nobody else is. Right, so I don't think it's a number of parameters thing per se.
So nothing in that slide with the evaluation with forward transfer, reverse transfer, and number of parameters. Nothing in there really prohibits you from storing all the data that you've seen so far.
Correct.
And if you have something that is able to achieve forward transfer,
Yep.
you automatically have a way to achieve reverse transfer simply by training on all the data you've seen so far and then training on.
That's right. And so if you do that, your computational costs scale with J squared, where J is the number of tests.
Yes, no, yeah, I agree.
And what we're doing, it scales linearly with J. And so you go from a quadratic cost to a linear cost. And I think that's a big deal in general. I would also say, I have a slide on this later, but basically, if you don't make any assumptions about the nature of the test, you have to increase the capacity as you get new tests. Otherwise, you'll just run out of capacity because there's new stuff. And there's really nothing fundamental about multiple tests. That's a property just when you have increasing data. Right? As you have more and more data, all the theorems say you have to increase your capacity to be able to fit arbitrary functions. And so, yeah, you have to increase capacity, and if you don't make any assumptions, you have to increase it linearly, and we did increase it linearly. So in a certain sense, I would say we've done the minimal amount of efficiency from a theoretical perspective, unless you make additional assumptions. Now, on these data, obviously the classes are highly related, and you wouldn't need to increase linearly, and that is very important future work. Okay, so I'm going to claim, we haven't proven this yet, but I think we'll be able to, that as a general rule, we can do this transfer efficiency if we apply this policy of partitioning space in such a way that each part has enough cells, each part is small enough but has enough points, then we can transfer from any one test to any other test. The reason that's going to be true is because even if the partitions from one test have no information about the other test, asymptotically, what's going to happen is they will add a 0.5, basically. They'll have no impact on the other thing. So it won't do worse if you have an infinite amount of source data. But it could do better. So what that is to say is if you have this kind of consistent transfer efficiency, with enough source data, you'll always get better, or at least you'll never forget. So that's cool. Just as a summary, I think in general we can think about learning as being done by partitioning and voting. Deep nets, as far as I can tell, do forward transfer. Lifelong forests can also do reverse transfer. There's no reason deep nets couldn't also do reverse transfer. And in fact, you can make a very strong argument that deep nets are implicitly learning a partitioning of space into polytopes. And people have argued this, and I think rightly so. It's a very natural way to think. If you use a ReLU activation function, then the ReLU is saying when you're on this half of space, you're one thing, and when you're the other half, it's a different thing. Right? And so deep nets are learning polytopes to partition space, as do what we happen to be using random forests to learn polytopes. And so, as far as I can tell, these same ideas could be applied to deep nets as well. I happen to not do very much deep network, so we didn't do that on this first paper, but I think it would be very natural to do it. And I also think all the theory that we would prove about the strategy of partitioning and voting will apply to deep nets and random forests the same way. So there's nothing special here about that. One thing that is important that highlights your question, most literature in deep nets, as far as I can tell, at least in practice, the architecture is typically fixed. And that's not what happens in even decision trees. The architecture is always changing as a function of the data. Now, there is obviously literature in deep network that says you should change the architecture with more data. And progressive neural nets is an example of that. But I think it may be something that deep net literature might want to take from the random forest literature, that if you're getting new tasks, you do want to increase complexity. Most of the literature on avoiding catastrophic forgetting now is really focused on not increasing capacity whatsoever. Which is a perfectly fine question as well. Like, how can you maximize the storage capacity for a fixed cell? But if you want to be arbitrarily general and be able to include more and more tasks, eventually you're going to have to grow. And the other thing I would say is partitions are just one kind of representing the data, right? So if you think about what a partition does, you take data, and now you represent it as a binary one hot string, essentially. So the data lives in this partition and none of the other partitions are non-overlapping. So it's a perfectly fine representation. I don't have any particularly good intuition why this kind of idea can't work with other kinds of representations that aren't so sparse or aren't partitioning per se. But it's just, we haven't thought about it like that yet. So I think it would be natural to do that. And then you have other kinds of algorithms like, say, support vector machines, where you know with certain characteristic kernels you can get universally consistent state regression functions. It's not obvious that they're partitioning in any meaningful sense. But they are implicitly learning a representation. So probably the theory could apply to that as well. Here's some references. Basically all the slides are in a paper that we're submitting today to ICML. So that link doesn't exist yet, but it'll exist in a few days. If anybody wants to see the manuscript, I'm happy to send it to you. We have another paper coming out shortly after on the theory. Those are papers that we've published on the preliminary work. All the code and everything is all in Python, and it's all open source and using sklearn, so it's easy to play with. I just want to acknowledge my family, a bunch of people at Hopkins that did a bunch of this work, and we've been recently collaborating with people at Microsoft that have been contributing a lot of code and ideas and applications. And all this work is funded by DARPA, and those are my kids. Thank you.
Questions?
Yeah.
So when you think about the idea of like, okay, you're talking about the graceful forgetting, right? And like, so maybe there's actually something where you want to have your kind of graceful forgetting rate to sort of match the actual true distribution shift that you see over time with new data. Is that something that you thought about at all?
Yeah. So there's something that is actually very confusing to me that I skipped because I don't know how to explain it, but I'll point it out. So XOR versus RXOR. RXOR has the optimal partition has no information. Right? But it's not that there's really no information about the two. Like, it's a one-dimensional parameter that completely characterizes RXOR given XOR. So I don't think I'm answering your question, by the way, but I just wanted to say this, and so now I'm saying it. You should be able to learn that from seeing the data, learn some kind of covariance shift, basically, and then not forget it all, in fact, doing reverse transfer. And so this has been a problem for me when I try to think about how to quantify graceful forgetting, because this problem where it is gracefully forgetting, it shouldn't be gracefully forgetting at all if you like take a step up and you actually have this abstract notion of tests and you can learn relationships between tests. And so that stops us from understanding the graceful forgetting so far. If you have a good idea about it, though, I would love to talk to you about it. I think it's a big problem for us right now.
Something's changed in regression, like in when you have quite many problems, geometry, physics, where we really regress for.
So, okay, so another thing I didn't say, because it's very exciting to me, is that the uncertain forest, which we're leveraging here, the uncertainty forest to estimate the posteriors, it has a bias for regression that I don't know how to get out yet. So we figured out how to make it unbiased, asymptotically unbiased for classification problems, but it's not even asymptotically unbiased for regression problems. And so we haven't pushed it onto regression problems yet because I just don't even understand what's happening. My feeling is it will probably work because it feels like a weird artifact of the theorem that there's a bias, but I'm not sure yet.
So we are going to have a quiz, I think, and we can meet
Great.
for an hour. And then we have a schedule for you. Thank you very much.
Okay.
Very interesting.
Thank you.
That's very clear.
It is?
I really learned a lot. I had discussed about this with Pratik.
Yeah.
I told him absolutely.
Yeah. Right, that example slide is because of Pratik, who told me, I didn't know Amazon cared about the code. I just thought it was a cool problem to solve. Yeah, I'm
I don't even know. I have forgotten the classification. I don't have regression for us.
yeah,
There are.
oh yeah.
We can talk about it.
Yeah, it's the same. It's what I said. It's for each cell, you just take that expected value.
Oh, you said, you take the other.
Hi.